We were dealing with the Euler-Totient function. The Euler-Totient function, which we met, this is the size of the multiplicative group of congruence classes, Zn. So Zn with the superscript times. Or in other words, this is the number of integers, a, between 1 and n, that are co-prime to n. Okay? These are the only ones that have multiplicative inverse. So we're interested in this function phi of n. It gives us the size of the group. And group is important in number theory, so knowing how large the group is important for us. We made we said that okay, you can evaluate the function phi of n working from the definition, checking all the numbers a between 1 and n, finding those that are co-prime to n itself, counting them. But that's quite a naive way to do it, just by working off the definition like that. We'd like something a lot stronger, which tells you what the value of phi of n is based on properties of the number n. And this is our theorem, okay, which we proved last time, and this is called the product formula for the Euler-Totient function. And it's a product formula for the value phi of n. So it's the product based on these elements pi and ai. The pi and ai are the primes and exponents that come from the prime factorization of n. Okay? So we consider the prime factorization of n. N is from the fundamental theorem of arithmetic, n can be written as a product in a unique way, essentially, of powers of primes. Okay? You know the prime factorization of n, you know the value of phi of n using this formula. Now this took a while to prove. Sorry. This took a while to prove. We based it on proving the special case of this formula for powers of a single prime. So we proved that phi of p to the power a was the appropriate value coming from this formula in the special case of just one prime, pi. Then we also proved that the function phi was multiplicative. So that being multiplicative meant that if two numbers were co-prime, if a and b were co-prime, then phi of the product a times b was equal to phi of a times phi of b. And then putting that together with this result about evaluating phi on powers of a single prime, that gives you the general product formula. And most of the technical work was in proving this result, that the function phi was multiplicative, and that took more or less all our time last week. So what we're going to do today is look at a few examples. Okay, so we like to see examples here. They're example problems. There are these two problems here in examples 5.1. Notes, page 36 in the notes. So these two examples here. So these are problems based on phi, and we're going to answer these by using those results about phi, using the product formula and using the fact that phi is multiplicative as well. So the first problem is going to be, we're going to prove when does phi agree on n and 2 times n. So when is phi of n equal to phi of 2 times n? We're going to prove that that's the case if and only if n is odd. And the second problem, well, it's just one example problem from many, an infinite number of problems like this. We're going to solve this equation for n. We're going to find all the moduli n that have phi of n equal to 12. So we're finding all the numbers n there, for which the multiplicative group of congruence classes modulo 12 is of size, so modulo n is of size 12. That's what we'll be doing when we're answering that question. Any questions so far just on that summary? So that's a summary of what we did last time, and then looking at these two examples. Any quick questions on the product formula or? Okay. So let's switch over to the paper and pencil, and we can work through some of these problems. Switches on. this first problem is to prove that 5n is equal to 5 2 times n, if and only if the other factor n is odd. It's an if and only if statement. So there's two directions to the implication. So we can prove it separately in both directions. So first of all, we can assume that n is odd. Assume that n is odd, and then we'll be trying to establish that 5n is equal to 5 2 times n. Now, please do stop me at any point if you want clarification on any of these points. So we'll consider 5 2 times n. Now what can we say about 5 2 times n? We know that n is odd. And I said at the start, the kind of tools at our disposal are the product formula for n, for phi, which is theorem 5.1, and one of the lemmas we used to prove that, which was that phi was multiplicative. Okay. Well, the multiplicative property looks appealing here, because if n is an odd number, it means n is not divisible by 2. So we've got the argument here written as the product 2 times n, but those two factors, 2 and n, they'll be co-prime in this case, okay, because the n is odd. Okay. So if n is odd, one way of saying that n is odd is to say that 2 and n are co-prime. Okay, because n, the only factors of 2 are 1 and 2, and if n is odd, it doesn't have a factor 2, so the only common divisor they have is 1, so the greatest common divisor is 1. But then we can use the multiplicative nature of 5 to factorize the phi value, phi of 2n, as phi of 2 multiplied by phi of n. So that's justified since phi is multiplicative. Okay, this is how multiplicative functions behave. If you evaluate them on a product where the factors are co-prime to one another, then you can factorize it as phi of one factor times phi of the other factor. Now, one of these we can evaluate. Not phi of n. I don't know much about n. I know that n is odd, but apart from that, I don't know much about it. But phi of 2 should be able to work out phi of 2. So who's going to tell me what the value of phi of 2 is? What is phi of 2? 1. 1 is the correct answer. How many numbers between 1 and 2 are co-prime to 2? Well, there's only 2 numbers to choose from, 1 and 2. 2 is not co-prime to itself, so the greatest common divisor of 2 itself. So the only number left is 1. So there's just a single element. So one congruence class in the multiplicative group of congruence classes modulo 2. That's just the congruence class of 1. So this is equal to 5n. Since phi of 2 is equal to 1 just by evaluating phi.
Could you just do that again? Phi n equals to phi 2 is equal to 1.
So why is phi 2 equal to 1? Well, just look back at the definition. Well, you can see it from the product formula, and you can see it from the original definition. The original definition is here. The Euler Totient function phi n is the number of integers a between 1 and n, such that a is co-prime to n. Well, you've got n equals 2, so the number of integers between 1 and 2. So there's only 2 to choose from. 1, 2. But this is you have to be co-prime to 2. There's 1 co-prime to 2, yeah. 1 is co-prime to everything. Everything has the greatest common divisor of 1 when it's paired with 1. But is 2 co-prime to 2? No. The greatest common divisor of 2 itself is 2. Yeah. So there's only one thing that qualifies then. So that's why 5 and 2 is equal to 5 and 2 is equal to 1. I mean, when you consider the integers modulo 2, you've got the integers, and you consider them modulo 2, you just get two congruence classes. Congruence class of 0 and the congruence class of 1. The even integers over here and the odd integers over here. There's only two congruence classes modulo 2, and the multiplicative group that you can form is actually just the trivial group. It's just the group consisting of one element, the identity element. So it's a pretty boring group. It's just one thing in it. The number 1, essentially. You can multiply 1 by itself, you get 1. So there's not a whole lot going on there. Pretty as simple as you can get. You know? So the result is satisfied. When n is odd, you get 5n equals to 2 times n. If that's just one direction of the equivalence, we should go for the other direction as well. So we'll now consider the other direction. So this time we've got to start off by assuming that phi of 2 times n equals phi of n. And we've got to reach the conclusion that n is odd. Well, how can we prove that n is odd? We can prove that n is odd by proving that n has no factors of 2 in it. Well, we can do that by doing a little proof by contradiction. You're trying to prove that n is odd is trying to prove a negative, trying to prove that it doesn't have any factors of 2. If you're trying to prove a negative or an absence of something, it's a little bit hard to get a grip on it with proving it directly. If we do a proof by contradiction, we'll be assuming n is even. So that will give us that then we can factorize n as 2 times something else and then maybe get some contradiction out. Okay. So assume phi of 2 times n equals phi of n. We want to show that n is odd. So a nice proof technique we can use is to do a little proof by contradiction here. Do this by contradiction. So we've got a little proof by contradiction within our overall proof here. So we'll assume n is not odd, i.e. that it's even. And from this, we're going to try and get a contradiction. What kind of contradiction? It's probably going to contradict this assumption here, assuming that phi of 2 of n is equal to phi of n. And that would be the. So we're going to assume n is even, work on that, work on getting consequences of that out, and come back and produce a contradiction to that. And that will show that this implies that n is odd. So you won't be able to have this assumption and the assumption that n is even coexisting at the same time. So that will prove that if this assumption is in play, then n must be odd. So that will prove the other direction of the overall implication that we're trying to prove. Now, if ever in number theory you assume something is even, immediately unravel that assumption. Okay? Assuming something is even means you're assuming it has a factor of 2. Okay? So you should immediately factorize it based on 2. So we can write n as, well, I could just write it as 2 times something, but let's fully factorize it based on 2. We can write it as 2 to the power k multiplied by n. So we'll suck all the 2's out of n. For some k We're assuming it's even, so it has at least one factor of 2 in it. So we'll assume we can write n as 2 to the power k times m for some integer k greater than or equal to 1. And we'll assume we've taken all the 2's out, and where n is odd. Okay, so we'll fully factorize it, but fully factor out all the 2's in it. We know there's at least one. Now this is what we're going to contradict up here. So let's look at 5n. 5n. Now we decided to write n as 2 to the power k times m. Now what should we do with this? Well, you see, I've just spelled out that we've got a bunch of 2's here, and n is an odd number. So these two factors are co-prime. NB, the GCD, 2 to the power k, and m is equal to 1. Okay, because m is odd. It doesn't have any factors of 2. The only divisors of 2 to the power k are other smaller powers of 2. 2 to the k and m co-prime. So we can use the multiplicative nature of phi here. Now, I don't know what m is. I can't kind of simplify this anymore, but I can certainly simplify phi to the 2k. I can use the product formula here. When you use the product formula on just a power of 2, you get 2 to the power k minus 1 times 5m. So that's by the product formula for phi. The previous step was by, since phi is multiplicative. Okay, so that's what 5n looks like. We've expressed it as 2 to the power k minus 1 times 5n. n is just some unknown odd number to us, so it's not like we can make much progress here. And just remember where we are. We're within a little proof by contradiction. We're trying to get a contradiction out. We're trying to contradict this earlier assumption that 2n is equal to 5n. Well, here's our expression for 5n, so we should try and get a similar expression for 2 times n. So now turn to 2 times n. 2 times n. This will be phi of 2 to the power k plus 1 times n. As before, we can split that up, because phi is multiplicative and n is odd. And this reduces now to 2 to the k times 5n. Okay? Using the product formula for phi of this power of 2 to the power k plus 1. The rule is you just reduce the power by 1 to get 2 to the power k. Are these two expressions equal? Well, no. K is at least 1. So here you've got 2 to the k, here you've got 2 to the k minus 1. So these are clearly not equal. This shows that phi of n is not equal to phi of 2n. But that statement now, we're now in contradiction with our earlier assumption. Okay. Phi of 2n is equal to 5. Here we've got phi of n is not equal to phi of 2n. Those two things are contradicting each other. Now, we didn't deduce this statement straight from this one up here. If we did, then we'd be showing that that assumption couldn't hold. If that assumption leads automatically to its own contradiction. That means it can't be true. But we made an additional assumption along the way. Along the way, we assumed that n was even. So it's this assumption that can't be made. This assumption can't be made because it contradicts the earlier assumption we just made. So we just need to explain that or point that out. This contradicts our earlier assumption that 5n was equal to 5 2n. The conclusion we draw from that is the intermediate assumption that n was even cannot be true. So we conclude that n cannot be even, okay, because that's the intermediate assumption. So n is odd. From beginning to end there, in this part of the argument, up here we assumed that 5n was equal to 5 2n, and down here we get the conclusion that n is odd. So we've shown that direction of the equivalence. So it's got a bit faint there. That 5 2n equals 5n. This implies that n is odd. So that completes. So it's a good illustration of using properties of phi to establish a nice fact about phi. 5n is equal to 5 2n, if and only if you're dealing with an odd number n. Okay. So any queries about that? Yeah.
If 2k equal to 2k minus 1, is that identical?
That's by the product formula. So come back to product formula, theorem 5.1. Well, the general product formula applies to products where you've got many distinct primes. But if it's only just a power of a single prime, so 5 2 to the k, we're applying this. So it's the version of the product formula when there's just one, when r is equal to 1. So just one prime. So 5 2 to the k is 2 to the k minus 1. And then you always have that extra factor, which is p minus 1. But in that case, it's just 2 minus 1. So it's just an extra factor of 1. So 5 2 to the k is equal to 2 to the k minus 1. And that, we spent time in the previous 2 lectures. We spent all our time establishing this formula in full, so we can use it now. Any other queries or clarification I can provide? Okay. All right, then let's look at the second of the example problems. Which is to solve 5n equals 12. And there's nothing particularly special about 12, except that it's an example. You could solve 5n equals anything. 12 is a nice enough example. It's not too easy, but it's not too complicated. So it's a nice middling example to illustrate the general approach. Right? So what we're looking here is we're looking for those moduli n which contain 12 numbers less than them that are co-prime to n. So it's quite, on the face of it, it's not a trivial question. We need to use everything we know about phi to solve it. So another way to phrase it is we're finding all the n such that finding all the integers n such that the multiplicative group of congruence classes modulo n is of size 12. It's another way to think about the question, think about the result. So the way we should approach this is to work from the product formula. Okay? So we'll base our approach on the product formula. Because we don't really know much about n at the moment, do we? Okay, we know 5n equals 12, but it doesn't immediately tell us anything about n. It tells us probably that n isn't that big. I mean, if n was a very big number, very big numbers, okay, there's lots of numbers less than them, and there's probably going to be lots of numbers less than them that are co-prime to n. The larger n is, the more chance things less than it have of being co-prime. You know, there's just more possibilities. So there's going to be lots of numbers there co-prime to n. So it probably seems like there's only going to be a finite number of solutions to this. But you know they can't be too small. Certainly n can't be less than 12. If n is less than 12, if there's less than 12 numbers less than n, so 5n is certainly not going to be 12. It has to be less than 12. So we're expecting some kind of middling range of numbers. Probably nothing bigger than 100. Surely something bigger than 100 would have many, many numbers co-prime to it. But n has to be at least 12. Anybody see one solution at the moment? Just 13. 13 is a prime number. We've already remarked that phi of p is p minus 1. So certainly, at least, that's a good observation, at least n equals 13 is a solution. Since phi of 13 is 13 minus 1. Okay. Well, that's good. Good observation to pop out. Okay. But are there any other solutions? Any other solutions come to mind? It's tricky. I mean, well, a couple spring to my mind because I know the answer, but it's not kind of obvious. So we need some systematic way, and it's going to be based on the product formula. Okay. So suppose, so not knowing anything much about n, suppose n, we'll start off by supposing that it has just a general prime factorization. So this could be any n, whatever. Any number would have a prime factorization that looked like that for some value of r, some primes pi. Then 5n by the product formula, well, I'm just really repeating the product formula here. Okay, so that's the product formula. So now, but that does help us rephrase the question again. So now the question is, when is 12 equal to this? When is 12 equal to that? Now this thing on the right-hand side is nearly a proper prime factorization. It's a product of a load of primes, but then you also have these other factors, pi minus 1, which are not primes in general, but they're even numbers. Well, let's just look at the factorization of 12. 12 is 3 times 4, so it's 2 squared times 3. So that has to be equal to, you know, well, there'd be a P1 to the A1 minus 1, P2 to the A2 minus 1, up to a PR to the AR minus 1, And then you have all these other factors, P1 minus 1, P2 minus 1, PR minus 1. So there I'm just kind of writing out this product, just with dot, dot, dots in the middle. Now, so this thing on the right is completely general, but come on, it has to be equal to 4 times 3. So that places an awful lot of restrictions on here. Now, it's not like we can quickly solve it. It's a little, it's still, you know, this equation, it's certainly not a link, you know, these are the unknowns over here. R is unknown, the number of factors is unknown, the particular primes are unknown, and the particular exponents are unknown. So you just got a single equation with all this unknown stuff on the right-hand side. So it's a very highly nonlinear equation. We're not just going to solve this in one go and, you know, immediately write down all the solutions. But what we can do is get some necessary conditions. So surely we can chuck out most of the possibilities here. Well, first of all, think the only possible primes Pi here are, what possible primes can we allow into the discussion? It's very restricted, since when you put the prime Pi in there, the only thing that can be produced here is one part of the factorization of 12. Well, certainly the prime 13 could be allowed, okay? Because 13 would produce the factor 13 minus 1, so 12 here, and that's part of this here. What other primes might be allowed? So what other primes could you allow in here which would produce factors on the right-hand side, which is C on the left-hand side? 7. If 7 were part of n, it would produce a 6 over here, which is allowed. Any more? 5. You could have the prime 5. That would produce a 4. 4 is on the left. Might as well keep going. 3.
You allowed 2?
Is he allowed 2? You tell me.
They give you a factor of 1, which is on the left.
Which is on the left, yeah. So there's no reason there's no definite reason to exclude 2. Maybe it mightn't arise. All I'm here, see, I'm just looking at consequences of this. So these are necessary conditions. They may not be sufficient. We can't allow any prime bigger than 13. No, we can't. What's the next prime after 13? 17. 17 can't be part of n, because if it was, it would produce a 16 over here on the right, which is too much to be contained in 12. You can't have any higher prime. Are these all the primes less than 13?
We missed 11.
We missed them. So why have we missed out 11? Should I include? Is 11 a possibility for being part of n up here?
No.
So why not?
Because 10 is not.
Yeah. If 11 was there, you'd see a 10 arising on the right-hand side, which would have a 5 in it, and there are no 5s here. So 11 can't be allowed. But all the other ones, 7, 5, 3, and 2, they are. Okay. So this immediately simplifies the problem. Because up here I was allowing any number at all for n. So I was just considering a prime factorization, a general prime factorization. Now at least I know I've simplified the problem a lot. It can only be based on these 5 primes. Okay. Okay, so let's just put a little note to explain what we've done. The only possible primes are these, since all other primes produce factors on the right-hand side not included on the left-hand side. Yeah? Do you understand what I mean there? We're considering primes, or we're excluding every prime which produces something on the right which you don't see in 12. Okay. And the only ones that don't fail that test are these 13, 7, 5, 3, 2. So now our solutions n must satisfy. I'm not saying these are all solutions, but all the solutions must fit into this pattern. It must be some power of A, some power of 3, sorry, some power of 2, some power of 3, some power of 5, some power of 7, and some power of 13. Those are the only primes that are allowed in the prime factorization of n. Now I've allowed general exponents here, A, B, C, D, E. Can you give me any quick restrictions on those exponents? Again, with reference back to this equation up here. Can we spot any easy, see at the moment I've just allowed them to be any exponents. For any quick restrictions?
C, D, and E aren't going to be bigger than 1.
Say that again?
C, D, and E aren't going to be bigger than 1.
Why not?
Because 5 is already producing 2 times 2. We can't have another factor of 2.
Yeah, or isn't it that, you see, if C was 2, then you'd have 5 to the 1. It would leave behind a factor of 5 on the right-hand side. Yeah, and there's no 5s. So yeah, so C can't be bigger than 1. And the same reason, 7 and 13, like you said, they can't be bigger than 1, because if they were, it would leave a 7 or a 13 or a 5 on the right-hand side, but there aren't any of those. So yeah, that's important. C, D, and E are an element of the set 0, 1. So that's the only possibilities for C, D, and E. Possibilities for B? Well, we could have B to the power I guess what I want to exclude is B couldn't be higher than 3. Or sorry, B couldn't be higher than 2. Because if B was 3, then we'd leave behind a 9 on the right-hand side. Because you'd leave behind a 3 squared on the right-hand side. But there's only one 3 here. So B cannot be higher than 2. Right, so B is an element of 0, 1, 2. And 2, or A, you can't have A bigger than 3. We could have a 2 cubed over here, because that would leave behind a, sorry, we could have a 2 cubed in n, because that would leave a 2 squared on the right-hand side, and there is a 2 squared here. But you couldn't have 2 to the power 4 in n, because that would leave an 8 on the right-hand side, but there's only a 4 in 12, not an 8. So A is an element of 0, 1, 2, maximum 3. So we've really, really reduced things down. N has to look like this, and there's severe restrictions on the exponents. C, D, and E can only, each of them individually only be 0 or 1, can't be anything else. B can only be 0, 1, or 2, can't be anything else. A can only be 0, 1, 2, or 3. That still leaves a lot of possibilities which we have to work through. Because if you took all the possible combinations there, it's, well, there's 8 possibilities here. It's 2 to the power 3. by 3 possibilities here, so 24 by 4, so it's 24 by 4, 9, so there's potentially 96 values of n covered here. Okay. Probably not all 96 are going to be solutions, but at least basically we're home and dry here, because up at this point, there's potentially an infinite number of solutions, but now at least we've capped it at 96. And we could at least go through every single one of those 96, evaluate 5, see if it's 12 or not. Then we'd find our solutions. But we can probably approach it a bit more systematically and quickly as well. So a maximum of 96 possibilities here for, did I work that out right? 4 times 24. Yeah, I think so. 96 possibilities for n here. We're already home and dry. Well, 13 is the biggest thing to exclude. Yeah. So there's one case which would have e equals 1. So then you'd have n equals 13 times n. The GCD of 13 and n was 1. So you could say 5n. Now we're supposed to have 12. But that is 13 times n. 13 and m are co-prime. See, m is representing all the rest of it here. So perhaps I could have a 13. M would stand for all the rest of it, which is co-prime to 13. So this would be 13 by 5n. So this is 12 times 5n. So that would imply that 5n was 1. Now, which numbers have 5n equals 1? There's only 2. 1 and 2. So that implies that m is equal to 1 or 2. Any number higher than 2, there's more than 2 numbers that are co-prime to it. Okay. Is that easy to prove? If n is bigger than 2, then the GCD of 1 and m, well, that's always equal to 1. And the GCD, you see, m minus 1 is always co-prime to n. 1 less than the number is always co-prime to the number, because there's a simple linear combination there which gives you 1. And if n is strictly bigger than 2, then 1 is not equal to n minus 1. So they are 2 distinct congruence classes. So that says 5n is strictly bigger than or equal to 2. So that's like a little aside here, justifying this conclusion. For any n bigger than 2, the 5n value is always at least 2. At least 1 and m minus 1 will be co-prime to n. So this gives us 2 solutions, the 13, which you found at the very beginning, but we also see m equals 2 as a possibility. So also 26 is a possibility. The two solutions are n equals 13 and 26. Okay, for n equals 1 and n equals 2. Well, that's fully dealt with the case e equals 1. So now you can assume that e equals 0. So that reduces the total number of possibilities now down to 48. 48 possibilities remain. Okay? Because this is one of the binary options is gone. So e can't be 1, e has to be 0. So now there's half as many possibilities left as before, which is 46. So we're even closer to the final solution. So, so now we assume e equals 0, and then you'd look at the next highest number, Now we consider the d. D can only be 0 or 1, so let's look at the case when d is equal to 1, see what that throws up. Now we'll look at the case d equals 1. So in that case, n is equal to 7 times something, which implies that 12 has to be phi of 7 times something, and that's phi of 7 times phi of n. So that's equal to 6 times phi of n. Well, if this is equal to 12, that's going to imply phi of m equals 2. Well, that should be pretty easy to solve. Which m's have a phi value equal to 2? The only ones are 3, 4, and 6. You can get this from the product formula. Study the product formula and think, well, how can the product formula equal 2? Well, that's a very restrictive case. How can the product formula equal 2? Only for these cases, 3, 4, and 6. Any number higher than that is going to produce a phi value bigger than 2. Well, indeed, any number bigger than this has a prime factor. It either has a prime factor bigger than 3, or it's got a factor of 2 or 3 bigger than 1, and that will leave behind a phi value of something bigger than 2. So this gives solutions to the original problem. So n is 7 times each of these, so 21, 28, and 7 times 6 is 42. Okay, so we got 3 more solutions. These are all the solutions in the case d equals 1, so now we can assume d equals 0. We're finished now because we've ended. So from now on, so now we can assume d equals 0. And at maximum now, there's only, to reduce the possibilities by a half now, there's only, what there was 46, and now there's only 23 maximum further solutions to find, probably a lot less. So now consider the case C, around that. So continue in this way. Considering the possibilities for C. What exponents are remaining? C, B, and A. There's at most 23 possibilities left. Find out which of them produce phi values equal to 12. Reach the final solution. Okay, so again, that's a nice example of working with phi, exploring phi, using all the properties of it to solve some interesting problems. Okay then.